Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Picture this.
Okay.
You are standing out in the absolute dead of night.
Pitch black.
Pitch black. You are looking up at the sky and you're waiting for something, anything to happen.
Right.
And then, bam.
A flash.
Exactly, a flash, a cosmic firework going off.
But not just a normal one.
Right, because you don't just see one explosion. You see the exact same explosion, the exact same burst of light happening in 5 different places in the sky.
At the exact same moment.
Yes, at the exact same moment. And they are arranged in this this perfect geometric cross pattern.
Surrounding those two faint glowing orbs right in the center.
It looks like a glitch. Like the rendering software for the universe just stuttered and copied and pasted a star 5 times.
It is a really striking visual. I mean, it completely challenges your intuition about how reality is supposed to work.
It really does.
Because we are wired to believe that one object occupies one location in space.
Right. Basic physics for everyday life.
Exactly. So when you see 5 of them, your brain instantly wants to reject it.
It feels like science fiction.
It does, but we aren't talking about sci-fi today.
No, we are not. We are talking about a very real, very hard data discovery that dropped in February 2026.
A massive discovery.
Right. This is the story of SN Winny, or SN 2025 Winny, if we want to use the formal catalog name.
Winny is definitely easier to say.
Much easier. It's a supernova that astronomers caught in the act.
10 billion light years away.
10 billion, and it's appearing as 5 distinct images.
And while the image itself is beautiful, I mean, it really is a cosmic firework, just like the researchers called it, the aesthetics are just the bait.
They draw you in.
Exactly.
Yeah.
The real hook here is what this specific glitch in the sky allows us to do.
Because it's not just a stamp collecting exercise for astronomers. Right?
Not at all. This might actually be the solution to the biggest headache in modern physics.
We are talking about the Hubble tension.
The Hubble tension, the absolute crisis in cosmology right now.
It's basically a 100-year-old argument that has split the physics community right down the middle.
I feel like argument is almost putting it lightly at this point.
More of a standoff.
Definitely a standoff.
Yeah.
We have 2 very precise ways to measure how fast the universe is expanding.
And they're giving us 2 completely different answers.
Right. And they cannot both be right.
If one side is right, the other is wrong.
Or, even more excitingly, both are right in their own way, and our fundamental understanding of gravity or the early universe is just flawed.
Which would be huge.
It would rewrite the textbooks. We have been waiting for a tiebreaker for years.
A third way.
Yes, a third way to measure the cosmos that doesn't rely on all the baggage of the previous methods.
And that is exactly what SN Winny represents. It's the independent arbiter.
It really is the Goldilocks scenario. It's this 1 in a million alignment that lets us bypass the messy, assumption-heavy calculations we have been stuck with.
So in this exploration today, we are going to look at how we found it, the insane technology required to actually see it, and the geometry.
Actual time delay physics.
Right. The physics that turns a pretty picture into a literal ruler for the universe.
It's fascinating.
Let's get into the weeds then. We need to start with the object itself. SN Winny.
Right.
We mentioned it's a supernova, but you don't get visible explosions 10 billion light years away from just run-of-the-mill dying stars, do you?
No, you don't. This has to be something massive.
So what are we actually looking at here?
Well, a standard type Ia supernova, which we use a lot in cosmology, is very bright.
Right. They are our standard candles.
Exactly. It can outshine its entire host galaxy for a few weeks.
Which is wild to think about.
It is. But at a redshift of 2, which is the distance we are talking about here, roughly 10 billion light years, a normal supernova would be incredibly faint.
Barely a pixel on a screen.
Barely even that. But SN Winny is a superluminous supernova.
Superluminous. I always love how literal astronomers are with their naming conventions.
It's very practical.
It's like, well, it's a supernova, but it's super.
It does exactly what it says on the tin.
Right. So how much brighter are we talking?
These are rare events.
Mm-hmm.
They are 10 to 100 times brighter than a standard supernova.
Wow.
We're talking about a release of energy that is genuinely difficult to even comprehend.
So we have this absolute beacon of light going off in the distant universe.
Right?
But the light isn't traveling to us in a straight line.
No, it's not. And this is where Einstein enters the chat.
General relativity.
Exactly. General relativity tells us that mass curves space.
Right. If you put a massive object in the fabric of space-time, it creates a divot.
Oh, well.
The classic bowling ball on a trampoline analogy.
It's classic for a reason. Now, imagine rolling a marble, which represents a photon of light, across that trampoline.
Okay.
If it goes near the bowling ball, its path curves.
It doesn't go straight.
Right. It follows the curve of the trampoline. Now, scale that up to the cosmos. We have and Winny exploding way in the background.
10 billion light years back.
Yes, and directly between us and that explosion, sitting right in the line of sight, are two galaxies.
These are the lens galaxies.
That's correct. The gravity of these foreground galaxies is bending space so severely that the light from Winny has no choice but to curve around them.
Like a funhouse mirror.
Exactly like a funhouse mirror. But here is the key. The alignment is so perfect, the light doesn't just curve one way.
It splits.
It splits.
So it's taking multiple routes simultaneously.
Think of it like a river flowing around a large island.
Okay, I can picture that.
The water splits, goes around both sides of the island, and then meets up again downstream.
So the light from the supernova streams around these galaxies.
Taking different paths through the curved space-time.
And those paths converge at Earth.
Exactly. So when our telescope points at that exact spot, it catches photons arriving from the left path.
And photons arriving from the right path.
Photons coming over the top and so on.
And our brain, or I guess the camera sensor, interprets those different arrival angles as completely different objects.
Yes, we see 5 distinct images of the exact same event. This is what we call strong gravitational lensing.
Now, we have seen lensing before, right?
We have.
The Einstein cross is a famous one, where a quasar is split into 4 images.
Right, that's a very well-known example.
So what makes Winny so special? Why are researchers so incredibly excited about this one specifically?
That is a great question. You are right, we have seen lensed quasars.
Quasars being those supermassive black holes actively feeding in the centers of galaxies.
Exactly. They are incredibly bright, and they stay bright.
They are permanent fixtures.
Basically, yes. They flicker a bit, they have some variability, but they are always on.
Meaning they don't have a distinct start and end date?
Right. But a supernova is a transient event.
It explodes, it brightens, it hits a peak.
And then it fades away. It has a very distinct light curve.
And that timing is crucial for what we want to do here, isn't it?
It is everything.
Because if we want to measure the universe, we need a clock.
And go. We need a clock. And a supernova is the absolute perfect cosmic stopwatch.
That makes sense.
But before we get into the how of the measurement, we really have to appreciate the odds here.
Right, the rarity.
Sherry Suyu, who is a heavy hitter in this field over at the Technical University of Munich and the Max Planck Institute, she quantified the probability of this alignment.
I read that quote. She said finding this is, quote, lower than 1 in a million.
And that is not hyperbole.
Really?
Truly. You need a superluminous supernova, which is already incredibly rare on its own.
Right.
You need it to happen at the exact right distance from us.
Okay.
You need it to happen directly behind a galaxy that is massive enough and compact enough to act as a lens.
And you need to actually be looking at it at the right time.
Exactly.
So it's not just something you stumble upon while casually scanning the sky.
Not at all. You have to actively hunt for it.
And this was a long hunt.
A 6-year hunt. The team, including researchers like Stefan Taubenberger, spent years just compiling a list of potential lenses.
So they basically mapped out the sky and said, okay, here are a bunch of galaxies that could act as lenses if something happens to explode behind them.
That's exactly what they did. And then they waited.
It's like setting up a bunch of camera traps in the jungle and just waiting for a very specific, very rare albino tiger to walk by.
And not just walk by, but explode while walking by.
Right.
They were monitoring these candidates constantly, looking for a sudden blip of light.
And then in August 2025, the alert finally went off.
It did? The Zwicky Transient Facility picked it up?
That's the Wide Field Survey Telescope that scans the sky every night, right?
Yes, it picked up a transient event.
So when they pointed the big guns at it, did they see the 5 images immediately?
Well, not immediately.
Oh, really?
No, they saw that it was a candidate. It was a blip. But to really confirm the 5 images and see the actual structure, they needed the heavy artillery.
They needed the Large Binocular Telescope.
Exactly. The LBT.
That telescope is in Arizona, right? On Mount Graham.
Yes, it is. And it is an absolute beast of an instrument.
It has 2 huge mirrors.
2 8.4-meter diameter mirrors sitting side by side.
But even with a telescope that massive, you still have a huge problem to deal with.
The atmosphere.
Right, the atmosphere is the enemy of high-resolution astronomy.
It really is. It's turbulent. It's what makes stars twinkle.
And that twinkling smears out the fine detail.
Exactly. If you were trying to resolve 5 tiny points of light that are huddled really close together, 10 billion light years away,
The atmosphere just turns them into a fuzzy blob.
and you cannot do precision cosmology with a blob.
So they used adaptive optics.
They did.
I always find this technology completely mind-blowing. Can you break down how that actually works for us? Because it sounds like literal magic, like we just untwinkle the stars.
It is effectively magic, but it is deeply rooted in physics.
Okay, walk me through it.
They shoot a laser, usually a powerful sodium laser, high up into the atmosphere,
How high?
maybe 90 kilometers up into the mesosphere.
Okay.
This laser excites the sodium atoms up there and creates a glowing artificial star.
A fake star.
Exactly, a guide star.
So they have a perfect reference point. They know exactly what that laser spot should look like.
They know it should be a perfect sharp point of light. Right. But because of the atmospheric turbulence, the wind, the heat rising, the different pockets of air, the image of that laser dot gets distorted on its way back down.
It dances around.
Yes. And the telescope monitors that exact distortion thousands of times per second.
And then it corrects it.
In real time.
That is insane.
The telescope actually has a secondary mirror that is deformable.
Meaning it literally changes shape.
Yes. It has hundreds of tiny little actuators behind it that physically push and pull the thin glass of the mirror.
So it ripples the mirror.
It ripples it in the exact opposite pattern of the atmospheric distortion.
So if the atmosphere zigs, the mirror zags.
Precisely. It actively cancels out the blur.
That is brilliant engineering.
The result is that you get an image almost as sharp as if you were in space.
Like Hubble or JWST.
Right, but with the massive light-gathering power of an 8-meter ground telescope.
And that is how they got the first high-resolution color image of SN Winny.
Yes. It revealed those 5 bluish points of light perfectly arranged around the 2 redder foreground galaxies.
It's an incredible technical achievement just to get the picture.
It is.
But that image is what allows us to actually start doing the math.
The real work begins after the photo is taken.
So we have the object. We have the pristine data. Now let's talk about the actual problem this is supposed to solve.
The big one.
We mentioned the Hubble tension earlier, and I want to drill down into this because I think a lot of people hear, oh, the universe is expanding, and they just think, okay, cool, science knows that.
Right, they think it's settled.
They don't realize that we are actually in a massive crisis regarding how fast it's expanding.
It is arguably the most significant disagreement in fundamental physics today.
It's not just a rounding error, is it?
No, it is a glaring contradiction.
Let's define the terms for everyone. The Hubble constant, or h0. It's essentially the speed limit of the expansion.
It's the rate of expansion. It tells us how fast a galaxy is receding from us based entirely on its distance.
Okay. And the units for this are notorious.
Kilometers per second per megaparsec.
Which is a complete mouthful.
It is, but it makes sense when you break it down.
Let's do that.
Basically, it means for every megaparsec, you go out into space.
And a megaparsec is about 3.26 million light years, right?
Exactly. So for every 3.26 million light years you travel outward, how much faster is space itself expanding?
So if the number is 70, for example,
then a galaxy 1 megaparsec away is moving away from us at 70 kilometers per second.
and a galaxy 10 megaparsecs away.
Is moving away at 700 kilometers per second.
Simple enough concept. Measure the speed, measure the distance, divide the two, and you have your number.
In theory.
Why is this so hard in practice?
Because measuring true distance in space is incredibly difficult.
We don't exactly have a cosmic tape measure.
We don't. We have 2 main methods that we use, and they represent 2 completely different philosophies of looking at the universe.
The ladder and the CMB.
Right. Let's start with the latter.
The cosmic distance ladder.
Yes. This is the local universe method.
Yeah.
It's empirical.
Meaning it relies on direct observation of things relatively nearby.
Exactly. You start with objects close to Earth, where you can measure distance using simple geometry.
Like parallax.
Yes, exactly like how your eyes judge distance. You measure the distance to a nearby star. Then you find a specific type of star called a Cepheid variable in that same star cluster.
Cepheids are what we call standard candles, right?
Yes. They physically pulse, they get brighter and dimmer, and their pulse rate is directly tied to their intrinsic brightness.
So if you know how fast it pulses, you know exactly how bright it truly is.
And if you know how bright it truly is, and you measure how dim it appears to us here on Earth.
You know exactly how far away it must be.
Exactly. It's the inverse square law of light.
So you use the really close Cepheids to calibrate the slightly further Cepheids.
Yes. And then you look for Cepheids in galaxies that also happen to have type Ia supernovae in them.
Oh, okay.
You use the Cepheids to calibrate the brightness of the supernova.
And supernovae are much brighter, so you can see them much further away.
Exactly. Then you use those supernovae to measure distances to galaxies way, way out in the Hubble flow.
Where the expansion of the universe is the dominant force pushing them away.
Right. So it's a ladder.
Rung by rung by rung.
And that is its greatest weakness.
Because it has systematics.
Right. If your very first rung is slightly off.
So because of dust extinction, making the stars look just a tiny bit dimmer than they actually are.
Or metallicity effects changing the internal physics of the Cepheids.
That tiny error propagates up the entire ladder.
It compounds at every single step. It's like a game of telephone.
So what number does the ladder team actually get?
The team, led by Adam Rees and others, using this method consistently gets a number around 73 or 74.
73 kilometers per second per megaparsec.
Yes. They have refined this over and over for decades. They are incredibly confident in that number.
Okay, so hold on to 73-ish. Now let's look at method 2.
The cosmic microwave background.
The CMB.
This is the echo of the Big Bang itself.
Right. It's the oldest light we can possibly see.
It's the ambient radiation left over from when the universe was only 380,000 years old.
Basically a baby picture of the cosmos.
Exactly. The Planck satellite mapped this radiation with truly insane precision. We look at the tiny, microscopic temperature fluctuations in that early universe.
The little hot and cold spots in the map.
Yes. But here's the catch with this method.
There's always a catch.
The CMB does not directly measure the expansion rate today.
Because it's a picture from 13.8 billion years ago.
Right. To get the expansion rate for today, we have to use a mathematical model.
We have to plug that baby picture into our standard model of cosmology.
Lambda CDM.
And we just run the clock forward.
We simulate 13.8 billion years of cosmic evolution to predict what the expansion rate should be right now.
So one team measures the universe exactly as it is locally, and the other team predicts what it ought to be based on exactly how it started.
That is a perfect way to put it. And when the CMB team does that massive calculation, they get 67.4.
67.4. So we have 67 on one side and 73 on the other.
And the error bars are tiny now.
They don't overlap at all.
Not even close. The 67 team says, look, we are right, plus or minus 0.5.
And the 73 team says, no, we are right, plus or minus 1.
So we have a 5 sigma discrepancy.
Which in physics is the absolute gold standard for saying this is not a fluke.
It means the probability of this just being a statistical accident is basically 1 in millions.
So someone is wrong.
Either the latter people have a systematic error, they just cannot find, maybe they really don't understand dust, or they don't understand Cepheids as well as they think. Or the CMB people are using a broken model.
Which implies new physics.
Yes.
It means maybe the universe expanded differently in the past. Maybe dark energy isn't a constant force.
That is the incredibly tantalizing possibility.
But we can't claim new physics until we definitively rule out the errors.
Exactly. We need a tiebreaker.
We need a method that is totally independent of Cepheids and totally independent of the CMB model.
Completely fresh look.
And this brings us right back to SN Winny.
Time delay cosmography.
This is the third way.
Yes.
So how does it actually work? How on earth do we get a Hubble constant out of 5 blips of light?
It all comes down to geometry and time.
Okay.
Remember those 5 images of the supernova?
The ones bent around the galaxy.
Right. The light in each of those images took a completely different physical path through space to get here.
Path A, path B, path C, and so on.
And those paths have different lengths.
It's like driving from your house to the office.
Perfect analogy.
You can take the highway, which is maybe a straight shot.
Or you can take the back roads, which wind around.
The highway might be 10 miles.
And back
roads might be 12 miles.
And if you drive at the exact same speed on both routes, you arrive at different times.
And light always drives at the same speed.
Constant C, the speed limit of the universe.
So the light taking the shorter path through the curved space arrives here first.
And the light taking the longer path arrives later.
This means we don't actually see the 5 explosions simultaneously.
No, we see them in a sequence.
So image 1 brightens up in the sky. Then, maybe a few days or weeks later, image 2 brightens up.
Then image 3 and so on.
We are literally watching a cosmic replay.
Exactly. We measure those time delays. We could say Image A arrived exactly 20 days before image B.
That time delay is a hard, observable data point.
It is.
But wait, it's not just the physical length of the path that matters, right?
Right.
There is also the Shapiro delay to consider. We have to get a little deeper into the general relativity of it all.
You were absolutely right to bring that up. It's actually two effects combined into one delay.
Okay.
One is the geometric delay. Literally, path A is a longer physical distance than path B.
Got it.
The other is the gravitational time dilation.
This is the interstellar effect. Time runs slower when you are deeper in a gravity well.
Exactly. The light that passes closer to the dense core of the lens galaxy is passing through a much deeper gravitational potential.
So it has to physically climb out of that gravity well.
And that struggle slows it down relative to the light that passed further out where the gravity is weaker.
So the total time delay is a combination of how far did I drive and how much traffic or gravity did I get stuck in.
That is a perfect way to visualize it.
Thanks.
And here is the absolute beauty of this method. Both of those things, the physical distance and the depth of the gravitational potential, they directly depend on the overall scale of the universe.
They depend on the vast distances between Earth, the lens galaxy, and the supernova.
And those absolute distances depend directly on the Hubble constant.
Right, because the Hubble constant dictates the size and scale of the expanding universe.
Yes. So the core equation is basically time delay equals the time delay distance multiplied by the potential difference.
Okay.
We measure the time delay directly with our telescope by watching the flashes.
Check.
We model the potential difference using the mass of the lens galaxy.
Check.
The only variable left in the equation is the time delay distance. We solve for that, and boom, we extract the Hubble constant.
In one single step.
One step.
No distance ladder.
No calibration of standard candles.
No massive assumptions about the physics of the Big Bang.
It is purely geometric. Stefan Taubenberger, who is a leading member of the team, calls it the one-step method for a very good reason.
It cuts out all the middlemen.
It really does.
But there is a catch. There's always a catch in astrophysics.
Always.
You said we have to model the potential.
Right.
That means we have to know the exact mass of the lens galaxy.
Yes.
How do you weigh a galaxy that is 10 billion light years away? Because if you get the weight wrong, you get the potential wrong, and you get the Hubble constant wrong.
This is the absolute crux of the problem with this method. It is known as the mass sheet degeneracy.
That sounds ominous.
It is the nemesis of lens cosmography.
What does it actually mean?
Basically, you can imagine a mathematical transformation where you make the lens galaxy much heavier, but you move it slightly closer to us.
Okay.
Or you change the distribution of the mass within the galaxy, and it produces the exact same visual lensing image on our telescopes.
Oh, wow. So the image alone doesn't uniquely tell you the mass?
No. You could have a really heavy lens or a slightly lighter lens with a different shape, and they would look absolutely identical to the LBT.
And if you don't know which one it is, you can't solve for the accurate distance.
Exactly. To break this degeneracy, you need more data.
What kind of data?
You need the velocity dispersion of the stars inside the lens galaxy.
Meaning you need to measure how fast the stars inside that distant lens are zipping around.
Right. Because faster moving stars mean there's more gravity holding them in.
Which means more mass.
Exactly. And this is where SN Winny really, really shines compared to past discoveries.
Why is that?
Usually gravitational lenses are incredibly messy.
Because they're usually massive galaxy clusters, right?
Yes. Swarms of hundreds of galaxies, massive dark matter halos, huge clouds of hot X-ray gas.
Trying to mathematically model the mass distribution of a cluster sounds like a nightmare.
It is heavily lumpy. It's chaotic.
It's like trying to calculate the aerodynamics of a tumbling bag of rocks versus a single smooth sphere.
That is very accurate.
But SN Winny is different.
Very different. The lens in this case is just two galaxies.
It's a binary system.
Yes. Alan Schweinfurth and Leon Ecker, who are researchers at TUM and LMU, they pointed this out.
They built the mass model for it.
And they found it was remarkably clean.
It's a clean lab for physics.
The galaxies have very smooth light profiles. They are close to each other, but they haven't actually started merging yet.
So they aren't distorted and tidal stripped and messy?
No, they are just two massive, relatively simple objects sitting there.
So the modeling uncertainty is much, much lower.
Drastically lower. Schweinfurth noted that this specific simplicity offers an unprecedented opportunity to measure the expansion rate with high accuracy.
Because we don't have to guess where the dark matter is hiding in some giant complex cluster.
We can model these two galaxies with extreme precision.
I do want to push back on that slightly, just playing devil's advocate.
Sure.
You have two galaxies. Doesn't that make it a three-body problem? Or at least a very dynamic, complex gravitational interaction? Isn't a single isolated galaxy much easier to model?
A single isolated galaxy would be easier, yes.
Right.
But single galaxies usually are not massive enough to create this wide 5-image split.
You need a huge amount of mass to bend the light that much.
Exactly. Usually to get this kind of dramatic separation, you need a cluster. So finding a binary pair that is massive enough to act like a cluster, but simple enough to be modeled like individual galaxies.
That is the absolute sweet spot.
That is exactly why this is a 1 in a million find.
It's the Goldilocks zone of complexity. Massive enough to work, simple enough to understand.
Perfectly said. And because it is a supernova, the time delays are likely very short.
Like weeks or months.
Yes.
As opposed to lensed quasars, where the time delays can be, what, years?
Easily. Quasars are often lensed by those huge clusters where the path differences are enormous.
You might have to wait a decade just to see the flicker repeat.
Which is incredibly frustrating if you want an answer in your lifetime. With SN Winny, the whole show will be over in a year or so.
We get the answer quickly.
We do.
So where are we in the actual process right now? The discovery was announced in February 2026.
Right now, every available major telescope is tracking it.
Both ground-based and space-based.
Yes. They are furiously building the light curves.
They are measuring exactly when image A hits its peak brightness, when image B peaks, and so on.
They are gathering the raw observational data for the time delays.
And simultaneously,
they're using spectrographs to get that critical velocity dispersion data we talked about.
to properly weigh the two lens galaxies.
Exactly.
Okay, so prediction time. Let's play the game. What happens when the final number actually comes out?
Okay, let's look at the scenarios.
Scenario A, the number comes back as 73.
If the number is 73, or very close to it, it is a massive, massive victory for the local ladder team.
It totally vindicates the Cepheid standard candle method.
It completely suggests that the systematic errors they were constantly accused of having simply aren't there.
And it puts the CMB team right in the hot seat.
It means the standard model of cosmology, lambda CDM, is fundamentally missing something.
It means the universe we see today is expanding significantly faster than the early universe physics predicted it should be.
And that requires a major physical explanation.
Like early dark energy.
That's a popular theory. A burst of accelerated expansion that happened shortly after the Big Bang and then just turned off.
Or maybe dark matter interacts with normal matter in a way we completely fail to account for.
Exactly. It throws the door wide open to exotic new physics.
Okay, scenario B. The number comes back as 67.
Then the tables turn entirely.
It vindicates the Planck satellite data and the standard model.
It strongly suggests that our theoretical understanding of the universe's evolution over 13.8 billion years is actually perfect.
But it implies the ladder team messed up somehow.
It would strongly suggest that there is a local hole in our cosmic neighborhood, or a very stubborn calibration issue with Cepheids that we just haven't untangled yet.
It would be a huge blow to the new physics crowd.
It would, but it would restore order to the universe, so to speak.
Right. And then there's scenario C.
Let me guess.
The number is 70. Right smack in the middle.
That would honestly be the most annoying possible outcome for cosmologists.
The ultimate compromise candidate.
It wouldn't actually solve the tension. It would just muddy the waters even further.
It would mean everyone is a little bit wrong.
Which is possible.
Huh.
But honestly, any result is good.
Because it's a completely independent result.
Exactly. It's not just another team reanalyzing the exact same old Cepheid or CMB data.
It's a fresh look at reality itself.
And we should definitely mention this is just the beginning.
Because of the new observatories.
Yes, the Vera Rubin Observatory is coming online.
And the Nancy Grace Roman Space Telescope.
We are going to find many more of these lensed supernovae.
So SN Winny is the first of its kind to be this perfect, but it won't be the last.
Exactly. We are actively entering the era of time delay cosmography as a standard, reliable tool.
But SN Winny will always be the historic one.
The Pathfinder. The one that proved it could be done with this level of pristine precision.
It's really a testament to human curiosity and ingenuity when you think about it.
It is.
Think about all the steps involved here. Someone had to come up with the math for general relativity.
Einstein.
Right. And someone else had to physically build the LBT on a freezing mountain in Arizona.
Engineers had to invent adaptive optics using actual lasers to unblur the sky.
Astronomers had to painstakingly catalog thousands and thousands of faint galaxies.
And then, after all that preparation, we had to get lucky enough to catch a single star exploding 10 billion years ago. It really is a cumulative triumph of science. It requires every single piece of that massive puzzle to be in exactly the right place.
I want to circle back to that cosmic firework image one last time before we close out this discussion.
Sure.
We talked a lot about the hard physics, but there is something deeply philosophical about looking at that picture.
There is.
We are seeing the exact same event at completely different times.
Right.
We are seeing the distant past and the slightly less distant past all at the exact same moment on our screen.
It completely blurs the line of what now even means.
It does.
When you look at that image, you aren't seeing a snapshot of a single moment in universal time.
You are seeing a collage.
A collage of different moments intricately stitched together by gravity.
It reminds us that simultaneity is entirely relative.
The universe is a funhouse mirror.
A very strict, incredibly mathematical funhouse mirror.
Exactly.
So to quickly distill the takeaways for everyone listening who might have gotten a little lost in all the megaparsecs and gravitational wells.
It's a lot to take in.
We found a superluminous supernova, SN Winny, perfectly split into 5 images by the immense gravity of 2 foreground galaxies.
A very rare alignment.
And by precisely timing the delay between when these 5 images arrive at Earth, we can independently measure the expansion rate of the universe in a single step.
Cutting through the noise.
Which could finally resolve the Hubble tension, that massive discrepancy between how fast the universe is expanding nearby versus how fast the early universe models say it should be expanding.
A perfect summary. The universe provided the ultimate test, and now we are basically just grading the paper.
And those final results should be out within a year or 2.
We will be watching very closely.
I want to leave you all with a final provocative thought.
Okay.
We tend to think of the laws of physics as these rigid, unshakable things that are written in stone.
We do.
But the Hubble tension reminds us that our laws are really just our current best descriptions of reality.
They are models.
Right. So if SN Winny gives us a number that completely breaks the standard model, it doesn't mean the actual universe is broken.
Not at all.
It just means our imagination was too small.
It means there is a hidden piece of reality out there.
A particle, a fundamental force, a weird curve in geometry that we simply haven't discovered yet.
And honestly, isn't that exactly why we do this?
It's the anomalies that always lead to the breakthroughs. You have to follow the glitch.
Always follow the glitch.
So tonight, if the sky is clear, go outside, look up.
You won't be able to see S and Winnie, of course.
No, it's way too faint for your eyes. But you can imagine that light.
Light traveling for 10 billion years.
Splitting apart, racing itself around massive galaxies, taking the scenic route, just to land on a mirror in Arizona and tell us how big our home really is.
It's a very big universe out there.
It certainly is. Thanks for joining us for today's exploration. Keep questioning everything and keep looking up.
Goodbye, everyone.